Hello, we are a group of quantum material scientists working on neutron scattering here in CAMM of University of Tennessee Knoxville. Today we're going to talk something about how to use the neutrons to study quantum materials. Let's start with Professor Alan Tannage, who's going to give us some introduction about neutron scattering.
Okay, thank you very much, Yeshu. Okay, so I'm going to start off with the basics of neutron scattering. Neutrons are a unique particle. They're spin 1/2, and they're charge neutral. They're produced in reactors and spallation sources, and actually, the ones that we use for scattering travel at non-relativistic speeds, typically around about supersonic. They have de Broglie wavelengths, so it's a quantum particle, and the wavelengths of the neutrons match atomic spacings. Their energies match the condensed matter excitations as well, and can sample the excitations of materials from nanoelectron volts out to electron volt energy scales. So the properties of the neutron allow it to interfere in space and time with the atoms and spins in materials, and it's that allows us to probe quantum materials in a unique way. The cross sections are extremely simple. The neutron is a point scatterer from nuclei, and through the dipole-dipole interaction for spins, we're able to get a quantitative comparison to theory. By measuring the two-point correlation functions, either the density correlations, that's between the nuclei in the chemical structure, or between the spins, one spin correlated with the other spin, in the system, we're able to build up a really detailed picture of exactly what's happening at the atomic level, both structurally and dynamically. The top right-hand corner is a simplified scattering diagram, just showing an instant neutron coming in. It's a typical way an experiment works. It scatters off a sample and goes into a detector, a small bit of solid angle in the detector. And that's how we measure the cross-section of the neutrons that are being scattered. We can then convert that into up to 4-dimensional wave vector energy volumes. Fully quantitatively, we have to correct for instrumental effects and other effects, such as the spread of electrons or unpaired electrons that give us the spins over orbitals. But we can do that very readily and accurately, allowing these huge data sets that encapsulate a very large and broad range of correlations to be sampled and recorded. So when you've got these enormous data sets, you can also convert them, not just and look at them not just in wave vector and energy space, but you can also convert them into space and time as well. So we can look at spin-spin correlations, for example, in real space and time, so-called G of R and T. And that gives us additional insight into how quantum effects are actually happening in these materials. So why neutrons? Neutrons have quantum sensitivity. Their direct interaction with spins and nuclei enables the probing of entanglement and topology. So it gives us very deep insights into the kind of quantum reality in materials themselves. They're non-destructive in bulk probes. That's extremely important because neutrons are able to penetrate deep into materials, and so they're suitable for looking at real quantum materials in action. They have unique contrast. They're sensitive to light elements and also magnetic structures that are invisible to X-rays, and their time and length scales access the relevant coherence regimes for quantum coherence in materials, from picoseconds to nanoseconds and nanometers up to microns. So in the picture here is some data being compared to theory. It's actually a neutron scattering experiment on a quantum transverse Ising model material, cobalt niobate. And this gives an idea of the kind of experiments that we can do and how really high quality data can be recorded that gives deep insight in real materials and can be actually be compared very accurately with theory. So this material, we're able to drive in situ using magnetic fields right through quantum phase transitions. At these quantum phase transitions, we're able to realize quantum fractal states. And by driving just away from the quantum fractal state at the absolute transition point, a very small ordered effects, ordering effects, actually cause an extraordinary symmetry to be revealed, the E8 Lie group symmetry, the most complex symmetry that's observable in the universe. So this kind of very subtle, deep phenomena, quantum phenomena, is the hallmark of what neutrons are able to reveal in materials. So what can neutrons measure that's relevant to quantum materials? They can measure the spin dynamics and entanglement witnesses, which gives us access to coherent quantum states and also to the quasi-particles. Topological excitations in quantum order, the detection of exotic orders, like in Kitaev spin liquids, quantum criticality and decoherence. They can reveal fluctuation-driven transitions and dephasing. Structure-function relationships, that's extremely important for developing materials for real uses. We can correlate the quantum properties with the lattice features. And also field and temperature tuned states, enabling high field and millikelvin experiments to be done. We also have other environments that can be applied, like high pressure as well. And the top right-hand side is an example of a spin liquid material. It's a spin liquid candidate material, sodium ytterbium diselenide. This is inelastic neutron scattering, and it actually has the fingerprints of an underlying Z2 quantum spin liquid state in this plot here. So using advanced computation, we're able to do matches between the underlying quantum states and the quasi-particles with the measurements. And so another additional benefit of neutrons is that we're able to extract the underlying models, the Hamiltonian that's describing all the interactions in the system. On the bottom right-hand corner is a newer development where inelastic neutron scattering in particular, and neutron scattering more widely actually, is being used along with quantum information theory to build up a more in-depth picture of the nature of the entanglement in the actual system itself. So the way that neutrons are actually able to reveal things like entanglement in materials is comes about from the fact that these are quantum wave packets that are being scattered off, and they are interfering in space and time between different spins in the system. That's similar to what a Bell's inequality experiment does. And in fact, we can reconstruct neutron scattering into fundamental insights into, for example, the entanglement depth in the material, pairwise entanglement, and also the total entanglement using particular witnesses. And this is a current area of very active development at the moment. So down the road in Oak Ridge National Laboratory, we have two of the Department of Energy's neutron user facilities, the Spallation Neutron Source, which is the world's most advanced neutron source currently. It has world-class capabilities, in particular time of flight spectroscopy, extreme environments, and cold neutrons. The high-flux isotope reactor focuses very much on quantum materials characterization techniques, but it also has things like sophisticated quantum beam manipulation techniques where mode entanglement of neutrons becomes possible. And in fact, there's completely new possibilities that are being opened up with the technologies currently. These technologies allow very high precision measurements to be undertaken. Our advanced instrumentation is available for users. So the user facilities are linked to synthesis, modeling, and data analytics programs. On the top right-hand corner here is a picture of a so-called spin echo type experiment. This is using shaped magnetic fields to manipulate neutron beams as part of very high accuracy measurements, in particular for lifetimes of quasi-particles. On the bottom right-hand corner is an example of Kitaev candidate material, ruthenium trichloride, which is proposed to host non-abelian anyons. These are very important for future quantum technologies. The groundwork for ruthenium trichloride and generally for quantum magnetic spin systems is undertaken using neutrons. So very in-depth studies of this material were made at the Spallation Neutron Source at Oak Ridge National Laboratory. And what's shown in the picture here is actually a small-scale device for using geometric engineering of thermal Hall effects to actually show that the required edge states are in fact present in the materials. So there's a strong synergy between the kinds of experiments that are done with scattering and then on to the actual application of the materials. So there's a wide range of instruments available at Oak Ridge National Laboratory, all of which we use at University of Tennessee and can be accessed through the proposal system. Single crystal diffraction, that gives us the detailed chemical and magnetic structures. These are vital for functionality. Powder diffraction, that can detect disorder using pair distribution function measurements. It also allows the characterization of a wide range of samples, so we can do very systematic sample studies for optimization using powder diffraction. Diffuse scattering, this is a very powerful technique, allows the measurement of short-range order and is a vital, provides vital information on short-range effects, particularly in frustrated and competing systems. And that's closely related to the operation of devices because these short-range ordered states are the kinds of things that can readily be manipulated for physical effects and to do transduction. Time-of-flight single crystal spectroscopy. This is a central technique for understanding quantum behavior of solids. It's the closest thing we have in condensed matter to measuring a wave function. With this, you can identify and characterize quasi-particles and their interactions. The triple axis spectrometer is a reactor-based inelastic workhorse. It's suited to polarized and parametric measurements. Reflectometry. Reflectometry can measure states and interactions across interfaces, which are critical for quantum devices. And finally, small angle neutron scattering. That involves the measurement of large-scale structures and textures, such as skyrmions and mesons and materials. These are the basis for emerging spintronics. On the right-hand side here, two of the existing facilities are shown. That's the spallation neutron source for the first target station and the high-flux isotope reactor as well. But there's a proposal underway for a new source, a second target station, which is expected to be built by 2034. And it's going to bring completely new capabilities that are particularly important for quantum materials and will very strongly expand what can be undertaken, particularly in heterostructures and device configurations. Thank you very much.
Okay, thank you, Alan. So as we have learned from Alan, neutron is a very powerful tool that can produce very exciting science at the frontier. So how are we going to start a neutron experiment, and what is a neutron experiment going to look like? So now Emily's going to share with us some of her first-hand experience about this information.
Hi, everyone. I'm Emily, and I'm going to introduce how you can start a neutron experiment. So first, as Dr. Tennant mentioned, we know that neutrons are valuable national resources and expensive facilities. So in preparing your proposal, we want to properly identify the science problem that you are aiming to tackle in your proposed experiment. So one of the ways to do this is you could identify any gaps in the literature and how your proposed project will help to answer any of the outstanding questions in the field. And also you want to definitely emphasize in your proposal why neutrons are necessary to answer this question that you're interested in. And specifically, if the proposed experiment can be resolved using an easier or a more accessible technique, then your proposal will likely be rejected. So emphasizing the scientific importance and also the necessity of using neutrons to solve this problem is important in your proposal. Here I've just shown a few materials of interest or classes of materials of interest on the right that you could use as a starting point to develop your science problem. So firstly, you'll want to start with some preliminary characterization in the lab. So at IAM, we have several X-ray diffraction techniques that we can use. And here I've shown here's a powered X-ray diffraction powder diffractometer. We have one for thin films and also single crystal X-ray diffraction, and then also Lowy XRD for single crystal alignment. And the goal and the characterization of your samples is to demonstrate to the proposal reviewers that your request for neutron time is motivated and justified by your preliminary observations. And also you want to demonstrate that your samples are ready and that they're high quality. So also at IAM, we have in our user facility here a PPMS and also MPMS, so you can conduct magnetic susceptibility, heat capacity, transport measurements, and other kind of measurements. And of course, if you have any previous neutron results, you want to include that data in your proposal as well. So upon establishing the preliminary characterization and justification of your experiment, then moving on to how to submit a beam-time proposal. Here is a call for proposals that's upcoming this August. And if you check back to the Oak Ridge website regularly, you'll see that they regularly have call for proposals that you can submit to. And once you understand your science problem, you definitely want to get in touch with the instrument scientist that you're proposing to work with so that you can ensure the suitability of the instrument for your proposed experiment, and then also review any sample environment options available, such as if you need a magnetic field or low temperature, high pressure, and the like. The instrument scientist is your best resource in ensuring that your proposal will be set up for success. Because as I mentioned before, neutrons are a valuable national resource, so they're not taken lightly when the proposals are being reviewed. So overall, a good proposal should be well motivated, well justified, and also well planned. So next, I want to introduce the new user beam-time program, and I'll take you to this website here, which I have opened. So you'll go to SNS ORNL New User Beam-Time Program, and here you can see specifically catered to new users. Their eligibility requirements listed on this website, and you can also look at how to apply and the next steps for this proposal submission process. Additionally, if you're not a new user, but you would still like to submit a proposal, then you can just Google ORNL SNS proposal submission. And from here, this is a much more detailed step-by-step process for how to submit a proposal. As I mentioned before, connecting with the instrument scientist team is important early on in the stage of planning your experiment. And then you can see the other details that are required, including any preliminary sample characterization that you might need, registering for your account, creating a proposal, and then also most importantly, how your proposal is going to be judged based off of the content that you submit. Okay, so once you've submitted your proposal and the beam time has been awarded to you, you'll of course go into your guest portal to confirm the dates and the samples for your experiment. And then the next important step to conduct is to ensure that you have enough samples grown and that they're thoroughly characterized prior to your experiment. Depending on the kind of experiment, you'll need a relatively large sample mass. And if your samples are not that large, then you'll likely need to co-align samples if they're single crystals. So some details regarding sample preparation. At SNS, there is a Lowy XRD that you can use, or also at IAM, we have a Lowy X-ray diffractometer that you can use to align your samples. Additionally, there's a neutron diffractometer at CG1B of HIFER. And here are some examples of the sample alignment process. And once the single crystal sample is aligned, then you would want to securely transfer it to the beamline and also load it into the sample environment apparatus, such as a sample stick or a sample can. And here I'm showing one of the cryostats that's used in for measurements. Okay, some more details about the sample environment capabilities. I won't go too much in depth here, but if you go to the SNS virtual tour, you can explore some of the sample environment cages, and you can see some of the cryostats, magnets, and things like that. And then also through this virtual tour, you can see some of the beam lines as well, such as high spec as shown here, or neutron spin echo as shown here. So I'd highly recommend going to the SNS virtual tour site. Okay, so we've already established that the sample is well prepared and that it's loaded into the cryostat or whatever sample apparatus you have. So how to enjoy your beam time and how to enjoy the experiment. So first, you'll want to check the sample centering, so the height and the centering within the cryostat, and check its orientation as well. There are also various tools that you can use depending on the instrument that you can simulate the detector coverage to plan your experiments to maximize the time that you have at the beamline. So once you've made these plans, here's a preview of what it looks like inside of one of the beamline hutches. You can see that there are plenty of monitors to use, and you're going to be working there with your instrument scientists and also your team. And the monitors are all so that you can watch the data on the fly. So there are many tools that you can use to be able to watch the data on the fly, and I'll show you some of these in a browser in a moment. But firstly, OnCat provides a list of all the scans that you're collecting, and then depending on the instrument that you're using, there are different data reduction and visualization tools. And essentially, for neutron experiments, because they're all grouped into how the neutron, where the neutron hits the detector, and also the time in which the neutron hits the detector, you have to basically sort these neutron events into a histogram into momentum and energy space so that you can then look at this data. So I'm going to show you the OnCat and Mantid and also Shiver tools on the SNS analysis cluster. Here in OnCat, you can see that there are the instruments listed at HIFER and also SNS, and you can choose the instrument that you're conducting your experiment at. And then, for example, if you're on MagRef, then you would go to your, you would click on your experiment title, and then also click on runs. And here you can see that, well, this just says data run, but you can make the scan name as detailed as you would like. And you can see that there's a start time and date for when the scan was conducted, and you have other information about the scan as well, such as the detector angle, sample angle. You'll often find the temperature of the sample and things of that nature through OnCat. And once you have the scan information, then when you have reduced your data, you'll move over to one of the tools for your that are specific to the beamline that you're using. For example, here I've already reduced the data. This is Mantid, and this is a slice viewer that you can use. So basically, you're looking at the HHO and negative HHO momentum space here, and I'm just cutting through the L direction. So this is for a single crystal data, for example. And then also in Shiver, we can, after the data is already reduced, you select your MDE, and then you can specify the energy range and also the momentum range that you're interested in. Okay, so after the experiment is completed, or towards the end of the experiment, you want to ensure that you have a complete data set for this specific experiment, because again, neutron facilities are not accessible all of the time, and they're valuable resources. So you want to make sure that you did your due diligence in collecting a complete data set. For example, you want to check if there are any additional scans that you might need regarding temperature, different fields. And then you would want to collect background acquisition and also a standard, such as vanadium can, if you needed that as a reference. And then upon the completion of the experiment, you would then check the sample for any radiation so that it's safe to handle after the experiment has been completed. And then, as mentioned previously, the final data reduction, this is where you would select all of your scans that you need to reduce into one main MDE, and you would want to combine all the scans that have the same experimental conditions. And my colleagues here will talk more about the final data reduction as well. Okay. Additionally, there's also some automation that's happening at some of the beamlines. So I'll briefly show this video of an automation that's happening at demand at HIFER. And a lot of the beamlines are pushing for automation. So this is, you'll see more and more of this at Oak Ridge. Here you can see this is the sample environment with some of the magnetic field polarizing the beam around the sample itself.
So after a busy beam time that you have collected all the data, the next question to ask or the next task is going to be what kind of information you can get from the data. So what are going to be the data analysis tools that we can use to model the data and learn about the information. So Tianran is going to tell us about the large-scale neutron data modeling and analysis. Okay, Tianran.
Hello, I'm Tianran, and today I'm going to talk about the modeling and analysis of large-scale neutron data. Here I prepared this animation of large-scale neutron data. It contains a lot of information. Like from the elastic channel, you can see the diffraction patterns that are very sharp black peaks. And from that, we can obtain the long-range periodicity of the crystal structure. And if the system have some kind of short-range disorder, and we can observe diffuse scattering patterns in both the elastic and the low-frequency inelastic panels. And from that, we can get the short-range correlations and local disorder and fluctuations of the structure. And in the inelastic channel, you can observe the phonons that reflect the lattice dynamics, and it can be modeled by the atomic force constants. And if the system have some kind of unpaired spins, we can observe magnetic excitations and magnetic Bragg peaks. And we use a spin model with exchange interactions to do that calculation. So let's begin with the diffraction. And on the left figure, I'm showing a single crystal diffraction pattern of the 3D Bragg peaks in the reciprocal space HK and L. On the right, it is a refined crystal structure, and we can obtain the single crystal diffraction pattern directly from a Fourier transform of the crystal structure, incorporating the scattering cross-section, thermal factors, and instrumental resolution. One may think that probably we can directly get the crystal structure from the neutron data by doing an inverse Fourier transform, but that is not impossible. That is impossible because the neutron diffractions that give the intensity but lacks the information of phase. So what we usually do is called a structure refinement. That is to adjust the atomic positions, occupancies, and thermal factors of the crystal structure, and then fix the simulation result to the observed diffraction pattern. And if this system is not a perfect crystal but has some short-range disorder, then we usually observe that is called a diffuse scattering pattern, which is shown in this animation. And it's like a continuous cloud. And to simulate that patterns, we need to prepare a set of different atomic configurations. Like here in this figure, I'm showing the hydrogen disorder in different water crystal structures. And we need to do a Fourier transform on each set of structure and then average over them. And we can use that simulation to compare with the neutron data. So from here, we can see that the diffraction, it tells about the average position of the crystal. And this diffuse scattering, it tells about the deviation of the atom from the average positions. So next is phonons. On the left, I'm showing two frequently used interactions. It is a stretching interaction and bending interaction. In the stretching interaction, it's like an extension spring that resists the stretching, the changes of the bond length. And the bending interactions is like the torsion spring that resists the change of bond angles. To mathematically express this, we need to introduce the force constant matrix, which is the potential of the second derivative to the atomic displacements. And we can use first principle calculations to obtain the force constant matrix, or we can directly build it from the interactions, the parameters Kb and K alpha. So once we build this force constant matrix, we can solve an eigenvalue problem and calculate the frequency and phonon normal modes. So in the right figure, I'm showing the phonon band structure that is obtained from the force constant matrix. This red, green, and blue colors indicate the phonon polarization along the ABC axis in the real space. So next, I'm going to show the magnets. Here is a very simple spin model where these atoms, these magnetic moments are connected through the exchange interactions. And we can use the software like here, I'm using Sunny Julia package to simulate the static and dynamic structure factors. And there are these different panels that are using different exchange parameters. And these simulated results can be directly compared with the neutron data, the elastic and inelastic neutron magnetic scattering results. And we can tune the model parameters to fit the neutron data. Thank you.
So thank you, Tieran. So from Tieran's description, we know that we actually need a lot of computational resources in order to model and analyze the model neutron experiment data. So now Isaac is going to tell us about some unique computational resources that CAMM has access to. Okay, Isaac.
Okay, hi. I'm going to start with some more homegrown softwares. As you heard Tianran mention earlier, we have a collaboration with Los Alamos National Lab and UTK's CAMM under MRSEC to support the development of this Sunny software. It is based on the SUN group theory for linear spin wave theory. And as you can see from the top two plots, we have real inelastic neutron scattering data on the left, looking at magnon dispersions in, can't remember what chemical or material it actually is. It's on the GitHub. So this is all in the tutorials. You can code this up yourself by just going to GitHub and learning the code. But to the right of that, we actually have linear spin wave theory calculations performed using Sunny, and you can see a strikingly good fit between the two. It has other features aside from inelastic neutron scattering. It can also do elastic neutron scattering, and you can get a good idea of the spin configurations by kind of modeling it with, do I have a pointer? I don't have a pointer. In the middle of the screen, you can see a very simple antiferromagnetic spin ordering that can be extended into a very large dimensional ordering. And you can perform Monte Carlo simulations to dynamically probe how the spins evolve in the system. This is a unique software in the sense that previous software developments for linear spin wave theory fail in a lot of locations where Sunny does not. So you can see the comparison between the C++ MC phase software and the MATLAB SpinW software. Each individually do good at their own unique area, but Sunny is a broad encapsulating software that can do many spin dynamics. Along with spins, we also have electron dynamics, and this is uniquely a UTK CAMM development. It's in Smoky Suite. You can find that on GitHub as well. Dr. Steve Johnston's group, he, along with two postdocs and a few graduate students, have built up an entire quantum Monte Carlo framework, essentially involving analytic continuations for imaginary time integrals that are not possible in many different approaches. You can get some novel results from this. I just picked a few from his highlights, like the stripe ordering of the charge density wave phase in A-Coop, right? I should have put the metal down. And then to the left, we have valence bond states in a honeycomb lattice. Aside from the homegrown stuff, we also have access to a local supercomputing cluster under the National Institute for Computational Sciences, or the Advanced Computational Facility. Right now, the new one is called Isaac NG. It's got 240 nodes and over 15,000 cores, and it's directly linked to the computing clusters over at Oak Ridge. I shouldn't say directly linked. metaphysically, symbolically linked. We collaborate with them. We typically get the old OLCFs. They have the new ones. Top tier hardware. So I have up here if I can get to it. I have my terminal open with the cluster at UT logged in, and I've just listed all of the available modules that you could potentially call in to your particular account, I guess you could call it. And you have things from density functional theory to just file manipulation, artificial intelligence, TensorFlow, parallel processing. It's just so much you could do with these clusters. And we're actively contributing to it. We have people working with UT, we have people working with Oak Ridge, we have people working within CAMM, all to develop new softwares, utilize existing softwares, and kind of push the boundaries of quantum materials and neutron scattering. So I'll take that away, and thank you guys for listening to this, because if you're taking the time to watch this whole video, you must either like us or like neutrons.
Thank you, Asad. I hope you have enjoyed our video, and if you want to learn more about neutron scattering, and please feel free to get connected with CAMM.